Alrighty, good morning, lads and ladies. Welcome back to Calc 2. Last time we met this whole concept of converge and diverge, right? That an integral can converge, an integral can diverge. If it is a certain kind of integral, right? An integral where the question is the area being measured finite isn't immediately obvious. Of course, all the integrals we did earlier in the semester prior to Wednesday, the area was always obviously finite because that region was finite. But now we're looking at regions where sometimes they're infinitely wide. And today we're going to see some regions where they're infinitely tall. And you'll see the rules for wide and tall regions are pretty similar, and we'll use the same language. But there are some slight differences, obviously. So that's what we're going to be doing today. We're going to be talking about type 2 improper integrals. I do apologize. I did not get your homework posted Wednesday as I had intended to. I made it and then I left it sitting open here and I didn't schedule it. So I just scheduled that for you guys. And to accommodate the time loss there, I scheduled it to be due next Wednesday. But please do try to work it as quickly as you can. Do not wait till next Wednesday because we're going to be moving on. Next Monday, we're going to be talking about different shit. All right, so yeah, this is it. Homework 6 for you guys is up. It's just section 7.8. That's the improper integral section. And we're going to finish that section up right now. So this is MAC2312, section 004, that is Calc 2. And today is the 1st of October. So welcome to October, everybody. Let's hope that it starts to cool down a little bit soon. Today we're going to talk about more improper integrals. Let's see. So I'd like to help you kind of contextualize these things, to see them, see the new ones, the type 2s, in the same sort of context we saw the type 1s, and then to sort of help you understand why we define them differently. Maybe we'll begin by saying recall a type 1 improper integral an expression of the form could be like integral a to infinity f of x dx, or something like maybe negative infinity to a f of x dx, or in the gnarliest of all possible cases, integral from negative infinity to infinity f of x dx. And really, we've only seen how to handle the first one. But the other two, you handle the same way. This guy, you could play with him and turn him into something of this form. But I'll show you just a couple examples where we approach each of these directly. These guys are kind of nasty. There's a few reasons why an integral from negative infinity to positive infinity, where you're kind of going off in both directions, needs to be handled very carefully. And then we'll also talk about type 2 integrals. So the main point I want to make here is that these forms, all of which seek to find an area of a region which is infinitely wide. All right, so each of these integrals is measuring an area. They're each a definite integral, but they're improper, and they're improper in the sense that you're either integrating from somewhere all the way off to infinity or from -infinity all the way up to somewhere, or some combination of the two. So the region whose area is being measured by any of these type 1 integrals is an infinitely wide region. And that's why there's a problem, right? The infinite width of that region means you can't build a Riemann sum, because you can't cook up delta x, because delta x is supposed to be b minus a over n, which is going to be infinite for any of these. And that's why we had to treat them with a limit. So before I actually get into type 2 integrals, I'd like to just show you maybe one example of each of these sort of things and how to handle them. Before I do that, are there any questions from the material we looked at last time? I'm especially concerned about the language. So I'm hoping that you guys are getting more and more comfortable with the vocabulary and the language surrounding these things, because we'll be using it for a while. Okay. So I'm going to go on here. I'll say today. Let's see, improper integrals. That measure the area of regions which are infinitely tall. And these are called type 2 improper integrals. As you can imagine, a region whose area, region that's infinitely tall, this is going to come from vertical asymptotes. Trying to integrate over a vertical asymptote is where you're going to get a type 2 integral. But before we do that, let's just look at some examples of these. Something where we're integrating from -infinity up to a. So let's do like integral -infinity up to 1 of x to the x dx. All right, so based on what we did Wednesday, does anybody have a guess as to how I should get started with such an integral? If this was the integral from 1 to positive infinity, how would I get started? Well, how did we start each of the problems we looked at yesterday or Wednesday? In every case, we had to first write the integral as, let's see something in chat. Yeah, we need to write it as a limit, right? This integral, I can't do shit with it. I don't have a fundamental theorem of calculus for this integral. I don't have trig sub or u sub or integration by parts. All of my tricks fail on this because it's not a proper integral. So first we write this as a limit of a proper integral. Now, in this case, the lower bound is going off to -infinity. So we write lim r to -infinity and then integral r to 1, same sort of thing. And then the inside of the integral stays the same, x e to the x dx. So the big deal is that this is improper. This is a regular proper Riemann integral. So I can do all the normal stuff with this. And then we take the limit at the end. Okay, how do I do this integral? How do you integrate x e to the x? Very good. Integration by parts. So I set up my IBP here. Means I need to pick u and dv. Following my Lipet rule, u is going to be the polynomial piece, which is x. And dv is going to be everything else, which is e to the x dx. Remember, we're not substituting, we're doing integration by parts. Du is then dx, and v is e to the x. So there's all my integration by parts stuff, and I learned that this guy is equal to the limit as r goes to negative infinity. I'm going to open up a big curly brace here, because we're going to have to take the limit of all the stuff that shows up from this integration by parts. This is integration by parts with a definite integral, so you have to remember our bounds also. So this is going to be x e to the x evaluated from r to 1. That's u times v, minus the integral from r to 1 of v times du, which is e to the x dx. So we do the evaluation step and also take our antiderivative in the second piece. When r to negative infinity, this piece evaluated from between r and 1 will give me r e to the r. Oops, sorry, let me do this backwards. Sorry. Let's try that again. This piece. Yeah, the upper bound is 1. I started plugging in the lower bound first. That's wrong. 1 times e to the 1 is just e, and then we'll have minus r times e to the r. That's that first bracketed piece. And then this guy is the integral of e to the x from r to 1. So that's just this. And then before I take my limit, I'll probably go ahead and just evaluate that because it's easy. There is one limit in here that's going to be a little tricky. So this minus is this minus, and then from here, I'm going to have another minus, right? So when I plug in 1, I'll have e to the 1. And then I need to subtract what I get when I plug in r, but this minus is going to make that positive. So this will be plus e to the r. Obviously, the e's eat each other up. What does e to the r do as r goes to negative infinity? What does that very last piece do? Let's perk up a little bit, guys. I know it's Friday, but I need y'all to show me that you're engaging a little bit, paying attention. What does e to the r
become 0?
Yeah, very good. It goes to 0. All right. If you take e and you raise it to an extraordinarily large negative number, that's like 1 over e, to a large positive number, this is going to 0. Okay. So I'm left with lim r to negative infinity. The only thing that survives here is that negative r e to the r. And this is not obvious. So I want to pause for a minute and see if we remember how to handle this sort of stuff. We just said that this piece is going to 0. And this piece is going to infinity, right? As r goes to negative infinity, negative r goes to positive infinity. So this looks like infinity times 0. What is infinity times 0? Oh, I see we've got some stuff in the chat there. Yeah, 0 is a reasonable conjecture, right? You multiply anything by 0, you want to call it 0. Infinity, however, is the sole exception to that rule. If you multiply infinity by 0, you don't necessarily get 0. This is what's called an indeterminate form. So remember in class on Wednesday, I said you may want to look back at sections 2.6 and 4.4 in the textbook. 4.4 is where you, in Calc 1, are supposed to meet indeterminate forms, and the kind of standard tool for tackling them when you cannot do it with algebra, which is called L'Hopital's rule. But I can't apply L'Hopital's rule to this right away. Reason is that L'Hopital's rule only works for certain kind of indeterminate forms called indeterminate ratios. So I want to use L'Hopital's rule. And L'Hopital's rule says if lim x to a f of x over g of x looks like infinity over infinity or 0 over 0, then you can take the derivative of the top and the derivative of the bottom and try again. In other words, the original limit would be equal to the limit of the ratio of derivatives. This is the statement of L'Hopital's rule. But it requires that you're looking at a ratio, fraction, where both the top and bottom are going to infinity or both the top and bottom are going to 0. And that's not what I have here, despite this being a certain kind of indeterminate form. So does anybody know how you can take an expression like this and rework it into something to which we can apply L'Hopital's rule? I've got two choices. I can either leave the negative r upstairs and shove e to the r downstairs as e to the negative r. This will give me an infinity over infinity. Or we could write it as lim r to negative infinity, leave the e to the r upstairs and shove r, negative r downstairs as negative 1 over r. Now, I know which one I would rather deal with. I would rather deal with the first one because the derivative of e to the negative r is nicer than the derivative of negative 1 over r. And also the derivative of r itself is very nice. So this guy, when you differentiate top and bottom separately, becomes nicer than this guy. So these are our two choices. The trick to writing an indeterminate product as an indeterminate ratio is to take one of the two terms and shove it downstairs as its reciprocal. It's an algebra trick. So I want to reiterate, if this doesn't feel like immediately coming back to you from Calc 1, then you're in trouble and you need to go back and you need to remember how to do this shit. It's very important, not just for this section, but for everything we're going to be doing for this next chunk of the course. Improper integrals, sequences, series, and power series, will you be using this sort of stuff a lot. So I'm going with this guy because this one's kind of ugly. Okay, so let me just see here. I'm just going to copy this down here. I'm not going to do anything in this step, just copying down what I had in the previous step. What does this look like? As r goes to negative infinity, where is this numerator going? If you plug negative infinity in for r here, what do we get? Yeah, positive infinity. Thank you. Thank you. Negative infinity is positive infinity. What about the bottom? I'm going to go ahead and just read Coburn's answer again. It's also infinity. All right, negative infinity is positive infinity. E to the negative infinity is e to the infinity. This is infinity over infinity. So now we use, I'll show you the notation I like. I just put a little L apostrophe H over the equal sign in the step where I'm using L'Hopital's rule, because otherwise these look weird. It's like, why have you done what you've done? It looks very strange. But if you tell your reader that you're using L'Hopital's rule, they'll have a better chance of knowing what the hell you're doing. What does L'Hopital's rule say? It says, if your limit looks like infinity over infinity or 0 over 0, then you can differentiate the top, differentiate the bottom separately, not using the quotient rule, just derivative of the top over derivative of the bottom, and try again. So the derivative of negative r is -1. I'm differentiating with respect to r here. The derivative of e to the negative r is negative e to the negative r. And we try again. So as r goes to negative infinity, what does this new expression do? Well, the top is a constant. It just stays -1. Downstairs here, I have negative e raised to the power of negative infinity. So this would be, I'll write it out, -1 over negative e to the negative infinity, which is positive 1 over e to the infinity, which is 1 over infinity, which on any day is 0. So this whole apparatus, take a second to soak it all in, this whole apparatus comes out to 0. Just for my purposes and to help me decide pacing of the class, locate the reacts and give me a thumbs up react if you feel comfortable with L'Hopital's rule. You remember how it works, you remember how to use it. Okay. So the majority of us need a little bit more practice with this. I want to say again, right? This is a Calc 2 class. It's not a Calc 1 class, so I'm not going to assign you a homework from section 4.4. Right? I'm not going to do that. But if you go into the textbook, you can work as many problems as you want here. The answers to the odd number problems are in the book, a full discussion of indeterminate forms, all the different types of them, how to handle them. It's all right here, guys. It's all right here. And if you look in the review material section in the modules, I'm pretty sure I have some stuff there for you also. And it seems that the majority of us need a little bit of that. Oh, this is pre-calc. If not, I'll add some. Oh, we don't. So we put it in the 7-8 stuff. No, I don't have anything in there. I just have these. All right. I guess I'll put it in the review material stuff. All right. So I'll find some. Some YouTube videos, some practice problems for you there. But the best thing for you to do, I'll say it again, is to go into the book. Go back to section 4.4. Look at all these problems. You work a third of these, then you'll remember it. All right. But if you don't, then you're gonna be in trouble. So like I said, we're gonna be using this stuff a lot. The same applies to section 2.6, the rules on limits at infinity in general. You need to be good at those. Okay, so we're not yet done with this problem. We wanted to work this integral. We found that it was 0. So what we would say is, that's the integral from negative infinity up to 1 of x e to the x dx. The language here, we would say converges, and the term is 2. That's the verb here. Sorry, the verb is converges, but I don't know what part of speech is. Converges to 0. That's how we would say it. So specifically, the integral converges, and the value of the integral is 0. Okay. So integral from negative infinity up to somewhere, really the same as integral from somewhere up to infinity. It's just the limit is a little different. It's totally possible that you run into L'Hopital's rule stuff like that in the types of improper integrals we were doing yesterday. I just chose the examples to be a little easier. The other thing I want to get you some practice with before we talk about type 2 integrals are integrals from negative infinity to infinity. And these are fun. It's a good example. It's a little too easy. Fuck it. No, I don't want to do that. That is too easy. We do need something that's bounded. Let me grab one from your book here because I don't want to. One example I have in mind. I don't want to save that. Yeah, we can do that. All right. Similarly unsatisfying, but no, that's fine. Okay. So with integrals from negative infinity to positive infinity, there's really two reasonable ways to approach the problem. So question, should we think of this as lim r to infinity, integral negative r to positive r, x e to the negative x squared dx, or lim r to negative infinity, lim s to positive infinity, integral r to s, x e to the negative x squared dx. So should I use two separate limits or one limit and work symmetrically? That's sort of the question. I think there's a lot of appeal to this. I actually really like this. This is called symmetric integration. But for us, this is what we do. We split the integral up, actually, and then we give each one its own limit. So let me actually redact this because this is going to look a little scary to you guys. I'll say, or should we split it into integral negative infinity to say 0 plus integral 0 to infinity and handle each separately. So the answer to this question kind of depends on what you want the word converge to mean. For us, we want to say an improper integral converges if and only if the area it measures is finite. It turns out that if you go with the first option, which to me is more appealing in a lot of ways, there are some integrals where this would come out finite, even though the area being measured isn't finite. There's like perfect cancellation, but both pieces are infinite. If you split integrals like this from negative infinity to infinity up into integral from negative infinity to somewhere, it doesn't have to be 0, plus integral from that place to infinity. This will be the procedure that yields the thing we want. We want the integral to converge if and only if the area being measured is finite. If you do it like this rather than like this, then it's possible to mess that up. So the answer here, we split it up. Because the first option can give finite answers even when the area is infinite. And I'll show you an example of where that first one can get you in trouble. But it's where you have like an equal amount of area above and below the x-axis, and even though both of them are infinite, they like cancel perfectly. That's where this thing can give you like an answer of 0, even though the area is infinite. So we're going to do the second thing. In other words, anytime you see an integral from negative infinity to infinity, and you'll see these in physics, and definitely in statistics if you ever take an advanced statistics class, you see something like this. The first thing you need to do is split it up. You don't have to split it up at 0, but you know it's nice to if you can. I could have split it at 1, or at 2, or at -5, or pi. Plus some negative x squared. And then each one of them gets their own limit, their own special treatment, because each one of those is a regular type 1 improper integral. So first guy I write lim r to negative infinity, integral r to 0, x e to the negative x squared dx. And the second one, you want to use a different letter here. S works. Lim s to infinity, integral 0 to s, x e to the negative x squared dx. And the antiderivative step here is the same for each, obviously, because the integrand is the same. It's a u sub thing. So these are both done. I'll use the letter z. We let z be, let's go with x squared. That way we're not orientation reversing. dz would then be 2x dx. We also need to change our bounds, so I'll do this on the sly here so we don't have to write everything out multiple times. When x is equal to r, z is equal to r squared. And when x is equal to 0, z is equal to 0. The x dx here is 1/2 dz. We'll have 1/2. And then e to the negative x squared is e to the negative z. And then similar stuff in the other guy. Lim s to positive infinity, this will become integral 0 squared is 0, s squared is s squared. And then again, we'll have 1/2 e to the negative z dz. Questions so far? Okay. So this will be lim r to the negative infinity 1/2. Antiderivative of e to the negative z is negative e to the negative z. And this will be evaluated from r squared to 0. And then we'll have plus lim s to infinity. Same antiderivative. This one evaluated from 0 to s. 0 to s squared, sorry. When you plug in 0 here, you get negative 1/2 times e to the negative 0. That's negative 1/2 times 1. So this is lim r to negative infinity, negative 1/2, and then minus negative 1/2 times e to the negative r squared. That's going to be plus 1/2 e to the negative r squared. We'll have something similar in the s piece when s to positive infinity. When I plug in the s squared here, I get -1/2 times e to the negative s squared. And then we need to subtract from that what we get when we plug in 0. So we'll have minus -1/2 e to the -0, which is +1/2. So the dominant piece in each of these is the exponential here, of course. As r goes, actually, let's look at the s integral first. As s goes to positive infinity, what is e to the negative s squared doing? If I plug a gigantic number in here for s, a gigantic number squared is an even gigantic-er number. So I have e raised to the negative of something huge. That's e to the negative infinity. So this piece is going to 0. I can write it out with the infinities if you want. Sometimes that makes life a little easier for folks. So I'll do the same for this guy. This will be e to the negative of negative infinity squared. And then I'll have plus -1/2 e to the negative of positive infinity squared plus 1/2, like this. And each of these are easy enough that this sort of trick will work. No indeterminate forms here, no L'Hopital rule stuff. This is -1/2 plus +1/2 times e raised to what power? Well, if you take negative infinity and you square it, you get positive infinity. And the negative of that is negative infinity. So this is e to the negative infinity. And then we've got -1/2. Same sort of thing here, right? If you square positive infinity, that's positive infinity. So this is e to the negative infinity. And then +1/2 here. And each of these pieces, e to the negative infinity, we know are 0. So this is -1/2 plus 1/2, which is again 0. Plus, we would say the integral from negative infinity to infinity, x e to the negative x squared dx converges, and again, converges to 0. And if we had done the symmetric integral -r to r, we would have gotten 0 also. So in the cases where the integral converges, you'll get the same thing using symmetric integration or splitting the integral up. But the symmetric integral can give you finite values even in the case where the integral should diverge. And somehow that symmetric integration process allows for nice cancellation to happen. Before I move to that, because I'm just hearing so little from you guys today, I'm kind of nervous. How do we feel about this problem? Give me some feedback. If it sucks, just say it sucks. If there's a part you don't get, just say I don't get it. Just let me know how you're feeling so I know how to pace the class. Any feedback? Is it easy? Is it hard? Is the notation weird? Spooky. Yeah, I agree. There's some spookiness to this. Definitely, it is a longer problem. Yeah. Any other feelings about this?
Is this going to be like a recurring thing that we will run into like a lot?
Improper integrals, yes. The question of symmetric integration versus asymmetric integration, not so much.
Okay. Just like where it ends up canceling out like this for that. infinite?
Yeah, so here what happened is this integral converged and this integral converged. So we started by splitting our kind of doubly improper integral into two simple improper integrals. This one converged to -1/2. This one converged to +1/2. So they were both convergent and they added up to 0.
Okay.
Let me, let's do some Desmos. So probably not a lot of us know what x e to the -x squared looks like. It's an odd function. Looks like this. And what we're doing here is we're looking at this blue area here. And this green area here. And it turns out that both of them are finite. Turns out that, you know, even though this little thing does go all the way out here, it gets so skinny over here that pretty much all the area is right here. And the same thing is true over here. And both those green and blue areas are finite. One of them is -1/2, the other one is +1/2, so they added up to 0. So this guy -1/2, this guy +1/2, both convergent. That's the important thing. And you might look at this and say, oh, well, it's an odd function. We're integrating over a region that's symmetric about 0. Of course it's 0. But let me mess with your intuition for a minute. Here's some question. Should the integral from -∞ to infinity of x dx converge or diverge, and why? In other words, is the area being measured? Finite or infinite? So like the problem we just did, the area was definitely finite, right? We split it up into two pieces, the green and the blue. Both of those pieces were finite, and they just happened to cancel perfectly and give us 0. But here, if I change f of x in that last example to just x, oh shit. Well, zooming out now. These are not finite areas, right? This is like very much not a finite area. And this is very much not a finite area. But if you integrate this symmetrically, then you will get 0. If you do this as lim r to infinity, integral -r to +r x dx, you absolutely will get 0 because this is lim r to infinity 1/2 x squared evaluated from -r to r, which is lim r to infinity 1/2 r squared minus 1/2 -r squared, which is, I mean, the thing, even without the limit, this is just 0, which is 0. But definitely both of these areas are infinite. That's a big full-bodied but. But the area bounded by f of x equals x from -∞ to infinity is very much not finite. So that's the question, right? This is really the way to look deeper at the question I asked at the start of the previous problem. Should we define this as the symmetric integral, or should we split it up as integral negative infinity to 0 plus the integral 0 to infinity? If you split it up, then you get both of those pieces diverge. However, the symmetric integral always gives you 0, because they say, okay, well, these kind of cancel perfectly. Right? If you look at just the integral from like negative 500 to 500, that cancels perfectly. And if you kind of allow it to grow out in a symmetric way, then you do get that beautiful cancellation and everything is 0. But since the total area here, the blue area is not finite, the green area is not finite, so the two areas together are not finite. So I don't want to say that this thing is convergent. We don't want to say that this converges. The way we do handle it, the correct way to handle this, is to say the integral from negative infinity to infinity of x dx, just like we did on the last guy, you split it up. So I'd say integral negative infinity to 0 x dx plus integral 0 to infinity x dx. And then treat each of these on their own with their own limit. Then r to negative infinity, integral r to 0 of x dx. And this is sort of why we use separate letters for each of these limits, right? R for the first one and S for the second one. And you'll see pretty readily, right? This is going to be then r to infinity, negative 1/2 r squared plus then s to infinity, positive 1/2 s squared, which is like negative infinity, and this one is positive infinity. So both pieces diverge. Sort of this guy on his own is a divergent integral, and the other guy on his own is a divergent integral. Both of those pieces diverge. And there's a kind of take-home lesson here for you, and this is that. So the upshot, I don't know if people still use that word, the upshot is this, and you should remember this. If any part of an improper integral diverges, then the whole improper integral diverges. So here, this improper integral, negative infinity to infinity of x dx, can be split into two pieces. Each one of those pieces is divergent. So the whole integral is said to be divergent. In other words, we don't allow this sort of cancellation of infinities here, which is incredibly dangerous. Can be done through the symmetric integration process. Some people call it Eisenstein integration. It's very useful in certain areas of mathematics, number theory, harmonic analysis, stuff like that. But we're learning the basics right now. We don't want to fuck ourselves up by saying you can cancel infinities and get 0, because it's certainly not always true. In fact, most of the time it's not true. And more importantly, the word converge here should mean finite area. This is not finite area. So this integral, the integral from negative infinity to infinity of x dx, whatever our definition of convergent is, we need to make sure that this thing is not a convergent integral because the area being measured here is super duper not finite. And this is the rule that allows you to get there in a reasonable way. You just have to remember, anytime you have multiple pieces that make it improper, like infinity at the bottom and infinity at the top, you split it up and handle each separately. You don't have to split at 0 like I did here. You could split at 1 or -1. But then if any piece of that improper integral diverges, the whole improper integral diverges. Okay? I see there's something in chat. Yeah, it's definitely possible to have an improper integral where one part of it is convergent and another part of it is divergent. I will show you an example of that, but I want to do it in the context of type 2 integrals. So let's first introduce type 2 integrals, work with them a little bit, and then I'll show you an example where you can split it up into one piece which is finite and another piece which is not. Okay. That's pretty much all you need on type 1 integrals. About type 2s. So again, a question. What is wrong with the following? Integral -1 to 1 of 1 over x. 1 over x squared. Yeah, let's do that. Dx. Okay. Well, 1 over x squared, that's x to the -2. So this is integral -1 to 1, x to the -2 dx. And an antiderivative for x to the -2 is -1 over x. So I evaluate that from -1 to 1, and I plug in +1. What do I get at +1? I get -1. Right? And -1, I get 1, so -1 over -1, like this. So this looks to me like -1 plus 1, which would be 0. Is that good? Yeah, okay. So is this okay? Did I do anything wrong here? It's -1, it's +1. This is what the graph of 1 over x squared looks like. So my integral should be measuring the area from -1 to 1. Uh-oh. You guys see the issue, right? What's wrong with this? Think with me for a minute here. Help me out. What's wrong with that statement? Yeah, there's lots of things wrong with it, in fact. So a few observations. First, all this area up here is above the x-axis. It should all be measured as positive. So there's no fucking way for this thing to be 0, right? You can't add two positive things and get 0. None of this area should be measured as negative. None of it is down here beneath the x-axis. It's all above the x-axis. So this is something positive. This is something positive. You add two positive things and get 0. That's not good. Also, and the main issue, this region goes up forever and ever and ever and ever and ever. Amen. This region is infinitely tall. Well, two positive areas shouldn't sum to 0. And worse, both regions from -1 to 0 and from 0 to 1 are infinitely tall. And we didn't account for that. I have a story around an integral like this. I don't know if you noticed the shirt I'm wearing is a Math Olympics shirt from, this was 2019, but way back in 2010, when I was an undergraduate, I competed in the Math Olympics, and they put a problem like this, not exactly this one, it was a little sneakier, but very much like this on the Math Olympiad, and I fucked up. I didn't realize that it was an improper integral, and I did exactly this, and I was like, oh yay, I got it, moving on. Easy, why would they even put that on there? Well, because it wasn't that easy. This is a type 2 improper integral. Integrals like these, you've got infinite height, are called type 2 improper integrals. And they require special treatment with limits. Like type 1. The problem here isn't that you can't build in a delta x, right? Delta x can be defined reasonably for this. The problem here is that f of 0 itself is undefined, right? This function blows up at 0. 1 over 0 squared does not exist. Max, hey, you got two choices. Leave the cat alone, you go back outside, motherfucker. Sorry. Out. So specifically, how do we handle these? What sort of special treatment with limits? Well, I'm not going to send r to infinity anymore. Instead, let me show you through a simpler example. Let's evaluate the integral from 0 to 2 of 1 over the square root of x dx. 1 over the square root of x also has a problem at 0, right? If you try to plug 0 into this function, the bottom is 0, which means the whole thing is undefined. And the graph of this function, his domain is just 0 to infinity, doesn't include any of the negatives as inputs, but the graph of this function looks something very similar to 1 over x squared. It looks about like this. So maybe I'll call this over here too. So the area I'm looking for is all of the area over here. And the way we do it is by dropping your favorite real number r over here, finding the area from r to 2, the dark shaded area here, which is definitely finite, and then taking the limit as r goes to 0 from the right, and we see what happens. That's the idea. So the way you handle a type 2 improper integral, if the problem is one of your bounds, like here, the problem spot is the lower bound, 0, you write this as lim r to 0, integral r to 2, 1 over the square root of x dx. There's one small catch here. I'm trying to integrate from 0 to 2. So I'm interested in this r walking to the left towards 0. I'm not interested in sending r to 0 from this side. I'm only interested in sending r to 0 from the right. So r is over here to the right of 0. I want to send it to 0 this way. That means this should be lim r to 0 plus. It's a one-sided limit. Pause for a second here, make sure we're comfy with why this is the appropriate setup for this problem. Specifically the one-sided limit. Are we okay with that? All right, from here, everything is what you think it is. That's lim r to 0 plus integral r to 2 x to the negative 1/2 dx. Calculate your antiderivative, then plug in the bounds, then take the limit. So an antiderivative for x to the negative 1/2, you add 1 to negative 1/2, you get x to the positive 1/2. So that's going to be 2 times the square root of x. Evaluated from 2. And at the upper bound here, we get 2 root 2. And minus the lower bound, we get 2 root r. And what does this square root of r do as r goes to 0 from the right? It's the square root function. So as I send r to 0 from the right, the square root of r is going to 0. So this is 2 root 2 minus 0, which is just 2 root 2. So we'd say that the integral from 0 to 2 of 1 over the square root of x dx converges to the value 2 root 2. This is an example of a convergent type 2 improper integral. The rules for converge and diverge are the same. If the area is finite, integral converges. If the area is infinite or doesn't exist for whatever reason, then the integral diverges. So with this in mind, let's revisit the problem we just looked at. So the correct way to approach the previous problem is to say, okay, integral -1 to 1 over x squared dx. 1 over x squared has a problem at 0. So just like the integral -infinity to infinity, you split this up as integral -1 to 0, 1 over x squared dx, plus the integral 0 to 1, 1 over x squared dx. And then you'd handle each one with their own limit. So I would say this is then r to 0, integral -1 to r, 1 over x squared dx, plus s to 0, integral s to 1, 1 over x squared dx. And each of these are going to be one-sided limits again. So here's 1 over x squared. That's -1. There's +1. And you would take r to be here, something like that. S to be here. That's the idea. And we're going to send r towards 0 from this side and s towards 0 from this side. So r is coming in from the left, s is coming in from the right. This would be r to 0 minus s to 0 plus. It turns out both of these integrals diverge. X to the -2 has antiderivative -1 over x. That part was correct. So this is -1 over x from -1 to r, and plus lim s to 0 plus -1 over x from s to 0. Oh, sorry, from s to 1. And when we look at just the first piece, I'm not even going to worry about the second piece. This is -1 over r plus 1 plus whatever over here. The limit as r goes to 0 from the left of -1 over r is what? What does this piece do as r goes to 0 from the left? So I'm going to draw the graph y equals -1 over r. Looks like 1 over x, it's just flipped over vertically. So as r goes to 0 from the left, -1 over r is going to positive infinity. So this is infinity plus 1. And, you know, the second integral piece is over here still. I don't even care about that because infinity plus 1 is infinity. So that first piece, integral -1 to 0, 1 over x squared dx, diverges. Hence, the whole integral diverges. you would find the same from the other piece. The other piece is also going to come out to plus infinity. So if you're not careful with these, it's very easy to miss the fact that a type 2 integral is even improper. Might not jump out at you right away, especially if the vertical asymptote isn't at one of the endpoints, at one of the bounds. So like here, 1 over x squared had a vertical asymptote at 0. So we don't even see the 0 here right away. 0 is between -1 and 1. So we are integrating over that vertical asymptote, but it's not going to jump out at you right away. And you need to think carefully. So when you're given an integral, you now have this new task. You have to ask yourself, is this an improper integral? For type 1 improper integrals, it's fairly obvious. Like one of the bounds will be infinity or negative infinity. But for type 2 improper integrals, they can be sneaky. They can be sneaky, right? A lot of people, if I gave this to 10 Calc 1 students, I bet 9 of them wouldn't even notice that there's an issue. Questions on this? Okay, how am I doing on time? We got time for one more example? Yeah, just barely. All right. Evaluate the integral from 0 to infinity of, how about 1 over 2x cubed dx. Okay, I need you guys to give me some input here. What sort of issues does this integral have? Why is this improper? Just waiting on you. I know you guys know this. It is improper. Why? This is one thing we see right away. It's making the integral improper. Why is it improper? Is it type 1 or type 2? Definitely there's type 1 stuff going on because of the infinity here, right? Infinity is one of my bounds. Yeah, so Frank makes a good point. This looks like a p integral. In fact, so did the last two, right? But remember, p integrals, the lower bound has to be a positive number, a to infinity, where a is greater than 0. So this is also type 2. Because 1 over x cubed has a vertical asymptote at x equals 0. So this is both. This is both type 1 and type 2. It has both sort of problems. We're saying I want to find all the area. 1 over x cubed again looks a lot like these other negative power functions. We're saying I want to find all the area under this curve from 0 all the way out to infinity. So there's a type 1 problem here. Sorry, there's a type 2 problem here, and there's a type 1 problem here. This is a type 2 issue. And the stuff down here, this is a type 1 issue. So the way you handle this is by splitting it up. And I think the natural place to split this is 1. But you could split it up at any positive number. So you want to separate the type 1 and type 2 issues. So I do the integral from 0 to 1 and the integral from 1 to infinity. And now, while the original is not a p integral, because for a p integral, this lower bound here would have to be a number strictly greater than 0. But this thing is a p integral. This is a convergent p integral. I would still need to find the value of that convergent p integral, but I know at least this piece does not diverge. Let's look at this piece for a minute. This is which is type 1. All right, this first piece, the p integral piece here is type 1, and this guy is type 2. This is a type 2 improper. So let's just look at each of them separately. Integral 0 to 1 over x cubed dx, we would write as lim r to 0 plus, right, thinking of r as being like here, going towards 0, integral r to 1 over x cubed dx, which is lim r to 0 plus, this is x to the negative 3, so his antiderivative is going to be x to the negative 2 over negative 2, or negative 1 over 2x squared. And we evaluate that from r to 1. So that's lim r to 0 plus negative 1/2 plus 1 over 2r squared. And I need to know now, what does this piece do as r goes to 0 from the right? Well, as r goes to 0 from the right, r squared goes to 0. So this is like 1 over 2 times 0. Negative 1/2 plus 1 over 2 times 0 squared, which is negative 1/2 plus 1 over 0. 1 over 0 is undefined. In this limiting case, though, we would say this is infinity. Take infinity and you add negative 1/2 to it, you still get infinity. If you want to be more careful, again, the like formal way to do this would be to look at the graph of 1 over 2r squared, which is very similar to the graph of 1 over r squared. So as r goes to 0 from the right, this piece is blowing up to infinity. All right, and now we're done. So even though this second piece here I know is convergent, I don't need to calculate it because this first piece here is divergent. And if any part of your improper integral diverges, the whole improper integral diverges. So let's say, therefore, integral 0 to 1 over x cubed dx diverges. Hence, the whole integral 0 to infinity 1 over x cubed dx is divergent. All right, and the idea there is if you were to look at this integral as two different pieces, what we did, you integrate from 0 to 1 and from 1 to infinity. The stuff to the right of 1 is finite. If you take all of this area, even though it's infinitely wide, the total area there is finite because this is a convergent P integral. P is equal to 3, which is bigger than 1. But the first part, the 0 to 1 part, is a divergent type 2 improper integral. So you take infinity, you add it to something finite, you get infinity. So the total shaded area here is infinite because the first chunk is infinite. So this is an example where one part of the integral diverges, the other part of the integral converges. All right. So you need to practice with this stuff. You need to practice with it quite a bit. You need to get good at spotting where there are issues, especially for the type 2 integrals. And if the issue for a type 2 integral is not at one of the endpoints, right, not at one of your bounds for integration, then you need to split that integral up to make one of the bounds the endpoint, or one of the bounds the problem point. Oh, I think that's all I've got for you guys here today. I think we're pretty Gucci on this. You do have, let me see, oh, that's right. Yeah, we didn't publish your homework yet, did we? All right, I will get that homework. Oh, no, we did. Yeah, I got it up. I got it up this morning. I just didn't have it up in time last night. Make sure. Yeah, your 7-8 homework is up. You're going to have until next Wednesday to do that because I was a little bit late getting this up. But it's got lots and lots and lots of improper integrals. And I want you to please, 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 as you do this, practice writing out the words, right? Practice making sure you're comfortable with the language and the tools that are involved here, because without those, the later sections are going to be very, very hard. So we're going to be moving from improper integrals to sequences next week. We'll move quickly through sequences and then start talking about series. Once we get comfy with series, we will start talking about power series. This is the hard part of the class. This is the part that gives COP 2 its reputation for being a difficult class. So please don't underestimate it. Put the time in. You need to study it every day, and you need to be talking about it with other people. If you don't have someone at home you can talk about it with, talk with someone on the Discord, talk to tutors, talk to your classmates. Just make sure that you're having some conversations where you're trying to use this vocabulary and get comfortable with it. Otherwise, you'll find yourself writing nonsense. It's like learning a foreign language, right? If you don't practice speaking that foreign language, ideally with a native speaker, someone who knows it well, then it's going to be very, very hard to even become conversant, let alone fluent. And we're looking for fluency here. We're looking for full-on fluency with this stuff. So please practice. And if you need help, come get help. I do have an office hour today from 1 to 2, so you can come talk to me there. Otherwise, I will see you guys on Monday.